So I was, I got up very early this morning, very, very early. So if I start speaking incoherently, it might be me, not the subject. Or maybe it's the subject. You can decide once you listen to this stuff. So here's a CPU graph on my MacBook Pro, it's got 4 cores and 2 hyperthreads per core. So you can see it looks like it's got 8 cores, doesn't really have 8 cores, it's got 4 cores. And you can also see that at the beginning of this, at the beginning of the graph, there's a fair amount of black. Right? Now black means that we're not utilizing the available hardware. So the core's there, but it's not being used. And you can see this on all the cores, 0, 2, 4, and 6, that at the beginning it is black, and then later on, once it's after about 10% or so, it starts going green all the way down. So what we're going to do today is we're going to get rid of the black and make it all green to look like that, so that we can utilize the hardware more efficiently. And actually this also completed a bit faster, about 8% or so. So as an example, we're going to work with some big numbers, just for fun. Now the numbers are a sequence called Fibonacci, most commonly. And Fibonacci is a very simple mathematical series to understand. It's basically f of 0 is 0, f of 1 is 1, and f of n is the previous 2 numbers added together. And it basically means that at every point we're almost doubling the size we had before. And this is why we have 7 billion humans in this world, right? Fibonacci series. And it's getting bigger very quickly. And the rabbits in Australia had a similar problem, that you're adding to the previous generation and it just gets more and more and more and more and more. And so the numbers get very large. And what a lot of people do is they take this mathematical formula and they produce a Java code that looks like this. Okay, they say basically public long f, and they say if n is less or equal to 1, then return n, otherwise return f of n minus 1 plus f of n minus 2. So this is very similar to the definition, the mathematical definition. But the problem that we have here is that we have to work out the lower numbers over and over, because it doesn't remember the numbers, it has to recalculate them. And as a result, we end up having the computational time complexity of the algorithm is in itself a Fibonacci series, which means it gets slow very, very quickly. So one approach would be to do it iteratively. So we have from 0 up to n, and we simply have to work out each number a single time. And this is great, except that we run out of numbers very quickly when we use longs. So with longs, we only can go up to 2 to the power of 63 minus 1, and at about n equals 93, the number overflows and we get the wrong result. So it doesn't really help us when you have the wrong result. So we get the result quickly, but it's the wrong result. Right? So we could use, in a way, BigInteger add, but the problem with the add function of BigInteger is that you're adding 2 big numbers together, and the add function is going to be, the cost will be in relation to the size of the numbers. So it's a linear cost of add, and a linear algorithm multiplied together gives you quadratic performance. You end up with basically order n squared bubble sort type of performance. So you can work out small numbers like this, but not very large numbers. Of course, this is much better than the previous one, which was this one, where you can't work out anything reasonable. Okay, so a third attempt is to use a better algorithm. Here's an example called Dijkstra's sum of squares. And what we do is we basically cut the numbers in half, and we have special formulas if it's an even or odd number to do the calculation. Now, I didn't invent this, I'm not that clever, but we'll code this in Java, and we'll code it with BigInteger. Unfortunately, we don't have operator overloading in Java, so we have to code it with like number dot multiply dot add dot whatever. It's really annoying, but that's what we've got. We don't have Scala in Java. Well, we don't. Operator overloading is not there yet. Maybe in Java 12 or something. So we've got this. BigInteger used to have a quadratic multiplier as well. So you end up with having order n squared cost of doing the multiplication. And this is sort of the multiplication you learn in junior school, where you take the two numbers and you multiply this by that, and and then you do it underneath and so on, until you end up with adding them all together and you get the total. The big integer since Java 8 has got better algorithms. The one is called Karatsuba. Karatsuba is not too difficult to understand. Basically what you do is you've got two big numbers, you split both numbers in half, and then you multiply the top by the bottom, and the bottom by the top and the other one, and then you combine them in some way. And the Karatsuba complexity is n to the power of 1.585. The three-way-Cook complexity is, three-way-Cook is a more complicated algorithm. It splits it into 5 bits, 5 chunks, and does some magic. Whoa, does some magic. See, must wake up. After lunch. But I don't actually understand that algorithm at all. I mean, that one is like completely beyond me. I've only got a PhD, so I don't understand that stuff. But what we will do is we're going to parallelize it in this demonstration. So prior to Java 8, this was order squared. Now we've got better time complexity, but it's still single-threaded. We're going to make it multi-threaded, parallel. Okay. So this is the first algorithm, and I want to just point out something. If I work at Fibonacci 1000 with the current code, which is going to look like, not this one, like this. If I work it out Fibonacci 1000 with this algorithm, I estimate it's going to take 10 to the power of 200 years to complete. It's an estimation, of course. I'm not going to try it out, right? We're not going to live that to try it out. That's a very, very long time. It's like 10 with 200 zeros years. That's long. And so we're going to get a win where we're going to get this Fibonacci 1000 done in a few milliseconds, like 10, 20, 30 milliseconds. That's going to be the biggest win we're going to see today. And you'll find this always with your code. Before you even think about making anything parallel or concurrent or threading or anything like that, you first think, can you do a better algorithm with better computational time complexity? And then use that instead. All right, so we're going to code what we just saw on the screen, which is this over here, in Java code. And this is how it looks. If first we say int half equals n plus 1 divided by 2, then we say big integer f naught equals f of n minus half minus 1. So at each point we're dividing by half. So it's a logarithmic time complexity, the actual algorithm. And then we do the same for f1 as f half. And then we say if n is odd, that's the first case. Concede if n is odd. Then we say return f naught dot multiply f naught, and then dot add f1 dot multiply f1. Now it would be nice if we could just say f naught times f naught, plus f1 times f1, but we don't have operator overloading in Java, so we can't. Else, we would say return. Now, how do you multiply by 2? Any guesses? Thank you. So we can say f naught dot shift left 1 dot add f1 dot multiply with f1. And you can see this is the same as what we have over here, the same algorithm. Okay. Now, if I did this correctly, which I hope I did, when we run the code, it should pass all the tests. And test 1000 finished in like 4 milliseconds. What would have taken otherwise 10 to the 200 years, now we do it in 4 milliseconds. Now that's the type of win you're not going to get with just throwing more hardware at it. So sometimes you have to think. That's the biggest lesson for today, I think. Now it's busy running, and I want to show you something whilst it's running. Here is top. Top is running. And you can see that Java is running at approximately 100%. Sometimes it goes slightly more, but it's typically around about 100%, which tells you that it's running single-threadedly. Even though I've got 4 cores on this laptop, it's still running with just one core, just on one thread. Occasionally it goes over 100%, and the reason is garbage collection. Sometimes it does a few GCs, and that it does with multiple threads. But most of the work is done just single-threadedly. So wouldn't it be nice if we could split this algorithm, because it's a recursive algorithm, into multiple branches, so that we can solve those independently. And if you look at this, whenever you're doing recursion, you can think about, could we solve this with a recursive task, which you can then put into a fork join pool. So you can do it in parallel. So both sides of the branch will be done by a separate thread, potentially, maybe, if that's what you want to do. So that's the next step, is parallelizing the algorithm. Okay, so the way this works is as follows. Whenever you have two recursive calls, you take one of them, you'd wrap it inside a recursive task that's an abstract class that supports the fork join pool, and then you construct that, you fork it, and this would potentially start a new thread or start it on a new fork join thread, and then you'd execute the other half of the recursive branch, and then you'd join with the first one that you forked. So if I've got two, I'd fork the one, execute the next one, and then join with the one I did before to get the results. So instead of just calling f half and f half minus 1, I'm wrapping it inside an object, forking it, and then later on joining together again. All right, let's try that and see if that makes it faster. Now, I've got 4 cores, so I would expect it to be quite a bit faster. So we're going to say recursive task over here of BigInteger, if not task equals new recursive task, and I'm simply going to take this code over here and move it in there, like so. Okay, and then I'm going to say down here, instead of saying BigInteger f naught, I'm going to say f naught underscore task dot fork, which will allow it to be executed inside the fork join pool. And after I've executed f1, I'm going to say f naught equals f naught task dot join. There we go. So fork one, execute the second, and then join with the first one again. Now, I've got 4 cores which can run at the same time, and at the moment, it's running in 44 seconds. That's the current speed. This is my current speed with the first exercise. I'm going to just put the comment in here so I don't forget that. That was the first step. I've got 4 cores. So how fast do you think this will run if I've got 4 cores? I know it's 8 hardware threads, but it's actually only 4 cores. About 20 seconds? 30? Why do you say 20? Okay, at every point, you're going to fork more. So you're going to fork, and then that one's going to fork again, and fork again, and fork again. So you're actually going to right. So you probably won't do that because I've only got 4 cores, right? You said 30 seconds. Why did you say 30 seconds? Well, we are, but then we're forking that half again. And both sides we're forking again. So the total forks are going to be far more. So before we actually, whilst we're running it, we're going to count how many forks there are, right? So we can, at the end, print out how many forks were there. So here's what we'll do. We're going to say return f of... No, we're going to do this this way. I'll make a long adder fork numbers equals new long adder, and then return fn comma fork numbers. Now what I need to do before I do that, I need to say big integer result equals, and then we're going to say print out fork numbers and return result. And then what we'll do in here is we'll say int n comma long adder fork numbers, and then we'll use those inside the calls to f. So here we've got f, it's going to be f comma fork numbers, okay, and there it's also going to be f half comma fork numbers. And then here we're going to say fork numbers dot increment, so we can count how many fork numbers are there. So for each case we'll see how many times was it actually forked, and you see that there's going to be, for example, for 100 million, I don't know how many, maybe 50 or so forks. I don't know, actually let's try it out. Let's run it and we'll see. So for example, a lot more than I thought. So for example, for 1,000 we have 755 forks. So really a lot of forks. Okay, it's because at every point it doesn't look right. It actually looks like it's too much. No, there's something wrong here, because it should be, yes. It should be. So fork number increment compute. Yeah, I'm not sure why it's not giving us the right number here. I would have expected it to be a lot less than that. Anyway, my point is it's not only two threads. It's going to occupy it should occupy all four cores at the same time. Maybe what we'll do is we'll do it a bit differently. Instead of doing it this way, we're going to print out the common fork join pool afterwards. There we go. Get rid of that. And this one, like so. And it's half minus 1 and half. So after every time, so what I'll do is for this very big one, I'll print out the fork join pool before and afterwards, which is this one here. Actually, I've done it already. Here you can see the fork join pool, common pool, before and afterwards. So let's run, for example, Fibonacci 1 million. It doesn't take too long. And why doesn't it print it? This one doesn't print it. Okay, this one prints it. So we'll do this one. Copy this up here. And there. Okay, so now you should see before and after that it does actually have lots of different tasks. Yeah, it doesn't show it. It shows the size. It shows the size, which is the number of threads currently active. It shows the number of steals. Unfortunately, the fork join pool doesn't give very much insight as to what's happening inside, how many tasks actually went through it. You can see the steals are quite high. So that's a significant number. Okay, let's move on. It's not running. It's not going to be 25 times as fast because I only have 4 cores, right? And if you run it, let's run the big one. What actually happens is that it's running. Initially, it's doing very well. It's running like it's 500%, 400% CPU. But as we go through the algorithm, it gets worse and worse. So it starts well, but then it ends up being, again, single-threaded. Right? And this is a very common characteristic you see in a recursive decomposition algorithm like merge sort, for example, because the final merge is what's taking all the time. So the problem we've got here, the reason why it's not not as much fast as we were hoping, it's not 4 times faster, but it's instead, it works out at at 22 seconds, which is actually pretty close to what you guys said. But your reasoning was wrong. That's why I wanted to ask you why you're saying the numbers. And it's pretty close, but the reason it's not better is because it's getting stuck on the last few calculations, which are taking all the time. So as we get towards the final number, you're dealing with very large numbers. And so that's where our time gets stuck. Right. Any questions? So what can we do about that? Well, we can parallelize the actual big integer as well. Now, before we do that, I've got something I want to give away today. So you've got to pay attention, because this is only going to happen today until 3 o'clock. I'm going to turn it off after 3 o'clock. So I published a self-study course on Saturday for people to do refactoring to Java 8 streams and lambdas. It's a lot of fun. And this is a code. If you go there, you can get it for free, but only until 3 o'clock today. Right, that's it. After that, it's going to be, I think it's 156 euros or something. So that's your chance to get it for free. I'll put it up again at the end, but at 3 o'clock I'm turning it off. So, okay, so getting his phone out. Can't do this. Right. You left time at the end to sign up. You don't have to do it right now. So what we're going to do is we're going to see if we can parallelize BigInteger. Now, the fun part with BigInteger is that inside there, they've got the algorithm called Tom Cook, which I do not understand. I haven't tried to understand it, but I don't know. I wouldn't understand it even if I tried. It's really complicated. And what we're going to do is we're going to change that. We're going to actually modify BigInteger. Now, you can do that also with Java 9, but it has another 2 steps that you have to take in order for it to work, and I don't want to waste the time on that. You just need to know that it is possible in Java 9. So, what we're going to do is we're going to only change Tom Cook. You could also change the Karatsuba, but we want to parallelize the very big numbers. With parallelism, you always have a threshold beyond which it doesn't make sense to parallelize further. So here we've got our multiply Tom Cook, and we're going to change that, and here's how we're going to do it. I've generated a separate package, a separate module for Java Math, and I'm going to go to BigInteger, and I'm going to teach you a technique that you can use for getting a really good score for your next code review. Right? If you want to generate lots of code per day, Command A, Command C, right? And then you go to your other directory, and you do Command V, and you've just written like 2,000 lines of code, right? One way to get really good code reviews. And what we're going to do is we're going to use this BigInteger instead of, we're going to change BigInteger and use this modified one rather than the standard one. Now, typically, if I put in here, for example, static print out, we are using the hacked BigInteger, you'll notice that it doesn't actually use the hacked integer if I call that. So if I run my test, you won't see that in the output. Okay, it's not there because we're not using the hacked BigInteger. But what we can do is we can go and change our command prompt, our command parameters to say -x boot class path /p, which means prepend the path to wherever this BigInteger is. Let me just make sure it's actually correct because I did change something. Yeah, this is actually the wrong one. So JDD Krakow. There we go. Okay, so it's now pointing to this modified one, and now it still hasn't done it. Okay, I'll make sure it's. Let me just make this again. make sure it's pointing to the right place. That's also wrong. So just 1 second while I fix it. It's going to be JDD Kharkov. And now it says we're using the hacked big integer. You saw that? That's the text we had at the top of a big integer. So it confirms that we're using this class that we've just hacked. Well, we're going to hack it now. Okay. And in Java, prior to Java 9, all you needed to do was to compile the class and put it into a boot class path, and you were done. Since Java 9, you've got to do a few more tricks. You have to patch and patch and patch and produce a patch and compile against a patch and so on. But you can still do it. So it doesn't go, you can still hurt yourself in Java 9. That fun doesn't go away. So now this trick I did with the recursive task, we're also going to do inside big integer, but I'm going to do it slightly more formally. I'm going to go to square tomb cook, and here I'm going to say private static class square task extends recursive task of big integer, and then this implements the method compute to return a dot square, where a would be your field, big integer, which of course would be final, and set in the constructor, like that. So that's my square task. My square task is taking a big integer and calling square on it. If you didn't know that big integer has a square method, it's a private method, but it is there. Right? And so what we do inside here is whenever we've now got a square, a square, a square, a square, a square. There are 5 different squares. They all have the same size. We can now say square task v naught task equals new square task of a naught. So a naught is going to get squared. Then v naught task dot fork. And then after we do the next square, and before we do the third square, we're going to say v naught equals v naught task dot join. So it's the same idea as before. We fork and we join, fork and join, fork and join. And then we do the same thing with v1. We say square task v1 task equals new square task of da1 this time. That's this one over here. Then we say v1 task dot fork. And again, before we exit from here, we're going to say v1 equals v1 underscore task dot join. Okay, so this parallelizes the squaring. So whenever we do a square, because a square is also a recursive method call, inside square it's calling square again. So now we're just doing, okay, we're going to do that, but we're going to do it possibly in separate threads. That's what we're doing here. And we're going to do something very similar with multiply tomb cook. We're going to have, with multiply tomb cook, see this is a very complicated algorithm, we're going to have a private class, static class multiply task extends recursive task of big integer. And then we're going to say private final big integer a comma b, set them in the constructor, and afterwards have the compute function to actually multiply them together. So compute is going to say return a dot multiply with b, like so. And then it's the same principle again. Before we do the first multiply, we're going to say multiply task v naught task equals new multiply task a naught comma b naught. That's the same as you have over here, these two. V naught task dot fork. And before we do the third multiply over there, we're going to join and say v naught task dot join. Same thing with v1. It's going to be multiply task v1 task equals, oops, don't want to do that, equals new multiply task DA1 comma DB1, and then V1 task dot fork, and then we do the other two multipliers. Once we've finished, we say V1 V1 equals V1 task dot join. Now, one of the reasons why this actually works at all is because BigInteger is effectively an immutable class. Right? If it was a mutable class, you're working with shared data, you wouldn't be able to do this at all because you'd have different threads working with shared data. You can't do this inside simple date format, right? That will not work. It's going to just blow up and give you completely wrong results. Okay, so now, hopefully we'll be able to keep all our cores busy. We want to see all the cores being at 400%, or all of them being 100%, so having a much more utilization of our available hardware. So let's run top at the same time. Oops. And you can see Java is now really utilizing our available hardware in a much better way. Okay. So this is great. This is what we want to see. And now we would expect it to be 4 times faster, maybe even better, right? But 4 times is what we should see. So it should be now sort of 11 seconds. Let's see how we did. Let's try it out. Let's go back to the code. And you can see that we're not quite there. We're actually at 18.5 seconds. We're not quite at 4 times faster. Even though I've got 4 hardware cores, I'm not 4 times faster. Any ideas why that would be? Pardon, sorry? Amdahl's law. No, not in this case. Not in this case. In other cases, yes, but not in this case. No, but the spawning of the threads is going to be relatively lightweight because it's only going to construct a maximum of 8 threads, including your main thread. So it's going to be 7 threads. No, none of that. None of that. What's happening is that when you're working out the numbers in a single-threaded way, or at least when you're doing it like this, parallel, you actually have a very high probability of working out the same numbers over and over again. And so, yeah, that's actually not the reason. So, yeah, there is an overhead as well. First of all, you're working out the same numbers over and over again, and secondly, you have the problem with what I want to say is as I said, I'm very tired. I've been trying to run the whole day. Yeah, so the way the algorithm works is that you work out with this. You're working out the same numbers repeatedly, which, as I said, in this case doesn't cause a problem. But you have also things like the garbage collector, which also kicks in there, which would affect the Amdahl's law, because you have a section where everything has to stop and wait for each other. Now that wasn't a very good explanation, but we'll move on to the next part. I want to show you a diagram which I think is quite insightful, which is this one over here. This algorithm looks like it would looks like the numbers would be relatively unique that we need to calculate, but they're not. They actually are the same numbers that we're working out over and over again. So you can see here, for the first level, you're trying to work out Fibonacci 1 million, for example, and then it splits it into 49999 and 500,000. But the next level, it's actually, you have to work the same number, so you're working out 250,000 twice. At level 14, you're working out Fibonacci 60 almost 8,000 times. And so when you combine the back again, there's a lot of numbers that are being generated, which are all duplicated. So this is where we can actually improve as well, is to cache some of the results. That'll give us a really big difference in performance. So let's try that. And over here where I've got Fibonacci, we're now going to do Fibonacci with a cache. Now, one way to do it is to put a static cache in, but if you do that, you're going to introduce most likely memory leak into your system. You don't want to ever have a static collection where you put things in and don't take them out again. So this is going to be comma BigInteger, comma map of integer comma BigInteger. That's going to be our cache. When we construct it, we're going to create a map. Now, it's going to be a map which multiple threads are going to be reading and writing data into and out. So it needs to be a thread-safe map. So, of course, we need to use a concurrent hash map. And so we're going to do this. Integer, comma, BigInteger, cache equals new concurrent hash map. We're going to seed it with 0 and 0. In fact, we're going to start with this if it's negative. Cache.put 0, comma 0. And cache put 1, comma 1. And then we're going to say return f of n, comma the cache. We need to just change all the places inside here where we're calling f. So it's going to be f of half minus 1, comma the cache. And the same thing inside here, half, comma the cache. And then we need to, of course, first check whether that is in the cache before we calculate it. Now, what's a good way to do that? What's a good way to only create it, to only call it when it's not there? Any ideas? So basically, I want to do this BigInteger results equals cache.getN. If n is equal to null, then I go, if n is results equal to null, then I go and work it out and put it in. So I say result equals cache.put n, comma result. And then return the result. Is there an easier way in Java 8 to do that? Computer for absent, right? Now, that's the obvious way to do it, right? I don't even know, maybe IntelliJ suggests it if I write this code. No, they don't. But it's an obvious way to, another way of writing this, seemingly obvious, is to use computer for absent, where you do this calculation inside a lambda, which then a supplier, or actually a function, which takes the n and produces a BigInteger. But there's a little catch with computer for absent. Well, there are two catches. One catch is that you're not allowed to change the structure of the map inside the compute function. If you do, bad things happen. If you do it with the concurrent hash map, you get an infinite loop. It doesn't ever exit. So something which seems like an obvious thing to do, which is I did this also, doesn't actually work. And in Java 9, they throw an exception when you try that. They give you, I think, illegal state exception or something. Right, so let's try run this now, and hopefully this is going to now compete faster, because we're not doing the same numbers over and over again. So we should get a performance boost. You can see a lot of GC going on. And we get down to 9.4 seconds. So that's actually more than 4 times faster. It's not as good as I hoped, because if you look at this diagram, you can see that a lot of the numbers we're really doing a lot of times. So I would have hoped for it to have a much bigger improvement than what we've got. But the challenge here is that because it's a recursive algorithm that we're going down in parallel, there's actually a very high probability that you have multiple threads working on the same number at the same time. Right? So you need some sort of scheme in which you can reserve things. Now, there's an obvious way of doing it, which is to do it with CompletableFutures, and I'll talk about that at the end. I'll give that to you as a job to do. I'll show you another way of doing it, which is where we actually put a placeholder into the map to say, if you see this placeholder, somebody else is working on it, just don't touch it until, just wait for them to finish, and then you get the result out. So we call this a reserved caching scheme. So let me just write down the number here. This is our, this actually was a nice performance boost. So now we're at more than 4 times because we're not working out everything over and over again. And if we now go and put this in, the idea is that instead of saying get, I'm going to say put if absent. So if the object is not there already, I'm going to put a special object in here called reserved. It's going to be a constant field, which I'm going to make a private final reserved equals big integer dot value of minus 1,000, for example. Some number that is not going to be a possible number in the set of numbers for for this series. And then the put if absent, if put if absent comes back with null, that means that we won the race to put the reserved in first. So after we've called null, after null comes back, the map now contains the value reserved. Anybody else looking at it sees, somebody's working, let's just wait for them to finish before we continue. So so if it's null, it means we won the race. We must start with the work. This stays mostly the same, except here I'm going to now do a try-cat, synchronized. I'm going to synchronize on the reserved. Of course, we can also do more lightweight. Okay, but there are not going to be that many threads who are going to be blocked on this. And then we're going to say reserved dot notify all. So anybody who's waiting on that will get a notification. Else, if the result is reserved, it means that we must wait. Then we're going to say try catch interrupted exception, EX, and we're going to say while result equals cache dot get n is equal to reserved. As long as it's still equal to reserved, we're going to say reserved dot wait. So we keep on spinning whilst it's equal to reserved. We keep on waiting until it's no longer reserved. Then we exit, and we've now got the value, and we can return that. If we get interrupted, we're going to simply say throw a new cancellation exception. Unfortunately, fork join pool really doesn't play well with cancellations. You actually need to have a separate Boolean, volatile Boolean that you use to notify for cancellation within the fork join pool. I tried really hard a couple of weeks ago to do cancellation properly with fork join pool, and I just couldn't get it working. You need to have like a separate flag that you use to notify. Oh, I got something wrong here. I didn't synchronize. Haha. So you need to also put a synchronizer on that. And now it should hopefully work. Okay, so now we are only working out each number a single time, which of course gives you, hopefully means we're going to do less work. And we have actually improved the performance quite substantially to 6.9 seconds. So we're only doing everything a single time. Okay, a couple of tips to make this really fast. Reboot your machine before you run the test. It's just amazing. It just really does work. Another thing which is quite funny, and let's see if you know the why, is when I first started with this experiment, I would copy and paste into my own package, into like eu.javaspecialist or something package. And it wasn't as fast as if I copied into the Java math package. Java math is faster than my own package. Any ideas why? Yeah? Yeah. It's not the class order. There's another reason within BigInteger, which would explain why. It's the same thing would happen if you copied strings somewhere else. Yeah, because it's completely different package. Yes, because it's a different package. There's something which string uses, which BigInteger uses, which it's called intrinsics. So some of the methods actually have special, like hand-coded C assembler code that is called. Exactly. For BigInteger specifically. So that's why it's so much faster. Now, as I showed you at the beginning of this, one of the interesting parts with this particular design now is that at the beginning of the run, you're actually going to have threads which are on the waiting state, quite a few threads. Now, on my machine, it's okay because I've got hyper-threading. It automatically makes 8 threads for my 4 cores. So it sort of still works. But if I turn hyper-threading off, I'm going to only have 4 threads, and I'm going to significantly reduce my parallelism of my code. So when I run the code, I'm actually out of time, so I'll do this quite quickly. When I run this and I put top on, you can see that at the beginning, you can't read too well. So let me do one more other test quickly, and that is to, that was too fast, that's why. Okay, we're going to do a quick thread dump, right? So the thread dump at the beginning, if you look, you'll see there are quite a few threads. These are common pool worker threads, which are in the waiting state. So that's 1, 2, 3, 4, 5, 6 threads waiting. We don't want that. We don't want threads waiting. So if you have threads waiting, you're not going to have the desired parallelism. When you construct your fork join pool, you specify how many threads you want to have actively running at the same time. That's your desired parallelism. What you can do is you can say that if a thread goes into the waiting state, it can send a notification to the fork join pool, or let the fork join pool manage it, so that the fork join pool can increase the number of threads and actually keep the parallelism the same, or at least high. And basically what you do is this part here where we're waiting, we wrap into a method, or into a special class. So I'm going to say inside here, private final, the class reserved blocker implements the managed blocker. This managed blocker interface is implemented by 2 places in Java. One is phaser, Java 7, other one is CompletableFuture. So managed blocker, with these 2, we're going to need private final int n, private BigInteger result, and private final map from integer to BigInteger, which is our cache. So we need a constructor for these 2, and then the result we're going to pass back once we've got it. Okay, now the block method, we're going to just say this code over here, return true. What block does is basically encapsulates this code here. But one of the tricks is to put the body of the while into the is releasable. That's basically like your condition predicate. So we read the cache, get into result, and if it's not equal to reserved, that means that we don't have to do locking. So here we're going to say, while not is releasable, wait. So that's not the same code, just refactored. Oh, it's so quiet now. I can hear a pin drop. Okay. So what we do in here now, instead of saying this try, we're going to say reserved blocker. Blocker equals new reserved blocker with the parameters. Then we say fork join pool dot manage block, and we pass in the manage blocker. If it's a fork join thread, it's going to manage the block and possibly construct additional threads. Okay, and then we say result equals blocker dot result, like so. Get rid of that, and now, if we're lucky, we're going to get better performance. It actually does make a bigger difference in the very large numbers. But because I've got only 1 million, it might not be that much of a deal. But on a billion, it is a bigger deal. So it's slightly faster. The difference is at the beginning. So I'm going to copy and paste this in here. You see it's a little bit faster. And I'm going to run it once more, and what I'm going to show you is the thread dump. So if you look for waiting, no, actually the common worker, we now have more worker threads. Before we only had up to number 7, 1 up to 7. Now we've got 11 inside there. So it's constructing additional threads, 12, to keep the keep the parallelism high within the fork join pool. Okay, so that's the last one. Now there's some homework for you to do. This is to implement the same idea with CompletableFuture. And there are 2 methods you can use to do that. Is then accept both async and complete. And what's also fun is if you turn off the common parallelism, the common fork join pool, if you don't want to have this, then you say parallelism equals 0, then it explodes with numbers of threads being constructed. If you try that out, you'll see. Send your answers to me, please, if you're interested. And I want to give you one more chance for this workshop if you want to get that. And now we can also have any questions if you have. Hyperthreading.
Yeah, because this is typical CPU-bound task.
Yes.
You use a CPU. If we, the hyperthreading works on the physical CPU as this hyper. Okay.
So the hyperthreading normally gives you benefits when you've got data
Yes,
bound
exactly.
algorithms.
Yeah,
right?
if I turn off a hyperthreading, I reduce half of my cores, but it's just a dropping of virtual cores.
Yeah.
I still have 4 workers, yes, but they use only one hand, not both.
Yeah.
It shouldn't be so bad in this case.
Right. So with the ManagedBlocker, if you turn off hyperthreading, it should be the same. It shouldn't be any worse. But it would be worse if you don't turn it off. It's because then you've got, you see, but because I've got two Java threads per core, it sort of still works most of the time. They are still quite busy. So that's a very good point. I must actually try turning it off and see how it works. Anybody know how to turn off hyperthreading in Mac?
It'd be us.
Yeah, so there's another thing with thread affinity. The idea is to keep each thread on a single core. Now again, you'll need to go over to Linux for that one. It won't work on Mac. But that makes a really big difference, because if you, and in many cases, if you go to single-threaded, obviously not with a number crunching like this, but in many cases when you go to single-threaded, you can actually improve your performance by just having a multi-core machine, but having just one thread on a single core, just doing one thing. It helps with latency specifically. Number crunching not, but for latency, yes. Any other questions? Yeah, why not use JMH? There's no reason not to use JMH. Yeah, I was just too lazy to code it in JMH. I don't like Maven, that's why. And I'm not sure how easy it's going to be to hack this new BigInteger into that as well. I'm not sure. Yeah. Well, it's a project. Another homework to do. Yes, sir.
Okay, so the question, could you please show this isReleased method?
Of course. Is releasable.
Or is releasable, yes.
This is just the condition predicate that we had. It's the if that we had inside the while loop.
Yes, so I see one very dangerous pattern here.
Yeah,
Side effects.
There's actually
result equal to. So this is actually something which I see since many years, and I don't know why do you see a reason of using a getter which is setting the value, but I would definitely avoid that.
Okay, now you have a good point here, and I normally talk about it, but we are short on time, so I skipped it. But I will talk about it, because the problem you have here is if there's a side effect, let's say for example that cache get sometimes gives after you've got the value, the next time you call it, it gets another value. It does work, but it wouldn't be, I don't think it would be safe, right, to do. Ideally, you should be able to call it isReleaseable 2 times without it generating side effects. So sort of a better approach would be to say return result is not equal to, is either
But just the main point that it's a getter, so it gives a value, but
Yes.
but it definitely shouldn't set any value. So the setting of the value is different.
Oh,
It should be in different place.
Right.
Yeah,
but,
so-
but there's another point also, which is if the method call here, let's say for example it would be a q dot poll, right?
Yeah, that's the same. It changes the
Then it
state.
changes it.
Yes,
Right.
and this is
then it doesn't work.
this is the pattern which generally should be avoided.
Yes, absolutely, absolutely.
There is
Thank you.
one other thing which I see synchronized. Is there any reason why you don't use Java util concurrent for logs, for example?
I'm not a great fan of Java util concurrent because it's too buggy.
Yeah, it relies on on the unsafe, the famous unsafe,
No, that's-
which is not a good
that
idea.
part's okay, but what I'm concerned about, first of all, a lot of people get the reentrant lock idioms wrong, and it's more subject to really weird bugs where, for example, you try and get a reentrant lock, and even though a lock is available, it still won't be released. You still can't get it, and other weird effects which. It doesn't happen as much with synchronized. If you and sort of there's been
That's a very good answer actually.
yeah, thanks. There's a trend back away from reentrant lock to synchronized. Inside concurrent hash map, they used to use reentrant lock. They've gone to synchronized. They've done the same with Java 9. Copy and write array list used to use reentrant lock. Now it uses synchronized. So if you've got the choice of both, and both will work, prefer synchronized because you have got less chance of bugs. And they've now, in Java 9, they've improved the performance of synchronized quite a lot, releasing and taking. Plus you get the hooks into the language for monitoring things like contention. All of these are reasons why I prefer synchronized.
Yeah, thank you very much for the explanation.
Thanks for the great questions. Thank you very much.